My name is Vincent Power.
I'm Brian McNulty.
I'm Chad McDowell. We're Network Power Monitoring, Group 22. The networked power monitor is a device that is installed into a house next to a breaker panel that allows consumers to monitor and control the power usage. This is done through a web application that gives the consumer a graphical tool to monitor the different areas of the home that usage is highest. Typically, consumers are only provided with their total monthly energy consumption by the power company. This device captures instantaneous power values that are stored for review at a later time. In addition, the device gives consumers the ability to remotely enable or disable the breaker. This additional control can be useful for disabling lights after leaving for work, checking if the stove is on, and turning it off, or anything else that is connected. From the standpoint of a utility company, the networked power monitor gives instantaneous power measurements and the ability to remotely disable devices. This can be tooled as a smart grid solution for demand management and allow the utility company to have some control for load redistribution throughout the day.
Looking at the top level block diagram, you can see that the microcontroller is at the heart of the device. It takes incoming data from the voltage and current sensing circuits to produce power values that contain both magnitude and phase. It also controls switching signals for the solid-state relays, which turn the breakers on and off. The LED indicators are driven from the same switching signal, and it provides red or green light to visibly show the status of a device.
The power supply is responsible for turning the 120 volt AC voltage from the utility into two different DC rails. A 5 volt rail and a 3.3 volt rail provide approximately 2.5 watts of power combined. The network controller sends and receives strings through UART to and from the microcontroller. The strings coming from the microcontroller contain power values, while the strings to the microcontroller contain commands to control solid-state relays. The network controller communicates directly with a web application via the internet, which is where previous and current power values are stored and displayed. The web application also stores a status that is changed by the user to determine if the attached appliances are supposed to be turned on or off.
The voltage sensing block provides both a voltage magnitude of the devices being powered as well as a phase angle of the house's AC power. The current sensing block measures the magnitude and phase of each of the three devices that are connected. All of this hardware is contained within the enclosure. This enclosure is a standard breaker panel box that allows for easy installation.
This is our network power monitor device. It currently controls 3 appliances. We have connected 2 120 volt outlets and a 240 volt outlet. It's installed in its own enclosure right next to a breaker panel. This is what you typically see in a house. You have your breaker panel, and then right next to it we can put our device. A little tour of what's going on over here itself. The circuit board here contains the wireless device, the Lantronix match port. It has an Atmega 128 microcontroller. There's some LEDs, sets of red and green, that indicate the status of the appliance, whether it's on or off. Red is off, green is on. Behind here, there's some Varus current transformers, and those give us the current measurement, the magnitude of the current. And right here, some solid state relays. This is what actually cuts the power on and off to our devices.
This is the web application, which is the main user interface for our project. As you can see, we have 3 gauges, one for each appliance that you're controlling. We also have 3 on-off switches, which allow you to turn the appliances on and off. If you go up here, we have an individual page for each appliance that displays the power usage over time.
For the purposes of this video, a wireless tethered cell phone is used as a router. The reason for this is because the university Wi-Fi doesn't allow direct communication between devices. In our case, the laptop is connected to the cell phone, and the match port is connected to the cell phone. The laptop also has a web server running, which is how the data is transferred through the web. The match port will send a HTTP post message to the web server, and the web server will respond with control signals for the power monitor to interpret.
Now for the sake of demonstration, I'm going to go ahead and turn on appliance 1. It takes about an 8-second delay.
For this demo, I'll show two devices being turned on and off. We have two 120 volt devices connected. We have a lamp connected to appliance 1, and we have a monitor connected to appliance 2 here. Currently on the website, it's showing that both devices are turned off. If I go ahead and turn appliance 1 on, which is the lamp, it'll take a few seconds to respond, and then the lamp will turn on. And if I do the same for the monitor, which is appliance 2, just turn that on and the monitor will turn on. You can see it's turned on the device, and the monitor has turned on. And if I go to appliance 1, once it loads, the power usage information will be displayed. So here's a graph of that, and you can see that we've been turning the lamp on and off, and it's using right around 30 watts. And if we go to appliance 2, which is the monitor, you can see that it's currently on, and it's also right around 30 watts too.
I will now talk about some of our unique design solutions. Our first unique design solution are our solid state relays that we chose. We chose solid state relays because they have a low power consumption, and they're able to be directly interfaced with our Atmega 128 microcontroller without a buffer in between. A second unique design solution is the Lantronix match port. It is a unified Wi-Fi solution that allows us to integrate directly with our Atmega 128 microcontroller using a UART bus.
Another unique design solution is the use of a MAX232 chip. This chip serves two purposes. Firstly, it serves as a troubleshooting device. As previously mentioned, data between the microcontroller and network controller is transferred via UART. With the use of the MAX232 chip, a DB9 connector, and a virtual COM port on the computer allows us to physically view the data being transferred between the microcontroller and network controller to make sure it's correct. The second use for the MAX232 chip is to provide negative voltages. As part of the current sensing circuit, there are transducers that output a small sinusoidal wave that's proportional to the incoming current. This wave is too small to trigger the zero crossing circuit used to calculate the power factor, so we require the use of an op-amp amplifier. Op-amp amplifiers require negative voltages. The MAX232 was an easy, efficient way of providing a negative voltage for that circuit. The one tip that I would have for people taking senior design next year is to take the first term seriously and spend as much time possible designing the top level diagram and designing all the individual blocks, because that's going to make your project go a lot smoother in the long run.
The main tip that I would suggest would be to take a development board or anything that you can that has to do with or is related to the project, and make sure you get the project working on that as well as you possibly can before you begin to build. If you can do that, then the process of building and submitting the PCB will go a lot smoother, because when it comes back, you'll already know it should work.
One tip I'd have is if you're going to design a PCB for your project, make sure you put test points and LEDs wherever you can on the board. This will help diagnose any problems that you might have with the circuits if they're not quite working right. It'll just give you a better look at what's going on rather than being stuck maybe cutting traces on the board when you really don't need to do that. If you have the test points and LEDs, you'll be able to see the problems a lot clearer.
We would like to thank our sponsors and donators, Pacific Corp, Texas Instruments, and Veris Industries, for their support and their donations.